Let's take a look at energy in magnetic fields. You recall that when we have charges in space creating electric fields, we had to do work to push all the charges together. And so if we look in terms of the potential and charge density in space, we found that the energy of the electric field was given by 1/2 times this integral here of the potential times rho. Now realize if rho is finite, so in space it is only included in a finite volume, then that makes this simple and that you only have to integrate over the region where rho is not equal to 0. We also express this in terms of the E field. So here we have E squared inside of the integral, and then the constant epsilon 0 over 2. So if E has a finite region, this would limit the volume over which you'd have to integrate. If it extends to infinity, then this integral has to go out to infinity. And of course, if this E field is dropping fast enough, then this integral will be finite. Well, we might be concerned about the energy of the B field because we've talked about B does no work, and so what does it mean to have this energy here? Well, we think of it differently in that if we had a solenoid and increased the current in that solenoid, we would actually be doing work against the back EMF that's generated by a changing current. So if we look at the time derivative of this energy, we can express that then in terms of the energy that we're putting into the circuit, which is the back EMF times the current. Well, the back EMF is related to the inductance in the case of a solenoid, and that is equal to L times di dt. And this I is repeated right here. So this is another expression for the time derivative of the energy, but we can rewrite this in terms of the time derivative of this quantity here. So what we find then, if we compare the arguments of the two derivatives, we can equate those, and we would have then that the energy of the magnetic field associated with an inductor with a current I flowing through the inductor would be given by this expression here. And this is a very useful way to do it. Well, let's continue and introduce flux. Now to do that, we just go to the definition of self-inductance here, which is the flux generated by a current I through this device. And so if we look at the flux in terms of the B field, we find it by integrating B over a surface S. Now just remember that's not a closed surface, so for a solenoid you could take a surface that just basically forms the cross section. So I'll try to draw it here. So you'd have this surface right here, which would be S, and you're integrating the B field that's penetrating that circle. Well, we can express B in terms of the vector potential. So remember that's the curl of A. So I've just substituted that in, and now we have a cross product which we can now use Stokes Theorem to get in terms of a line integral. So here we would have the line integral of A dot dl representing the flux. And the loop that we're taking, or the path, we could call C, is one through which the flux is passing. But we can also change the order of all of this. If we take a look at the energy now and express it in terms of 1/2 I times the flux, which is all of this right here, we can bring I inside the integral and put it right here multiplied by dl. So here we have A dot I times dl. Well, we're going to generalize this by introducing the current density. And to do that, we consider a current flowing through this region of space right here. It could be a wire, but let's just call it a region of space. And that region has a cross-section of dA and has a length dl right here. So if we look at the expression IdL, which is the component of I in the dl direction times the length of dl, we can write that as J.dA, that'll be the current, times dl. Well, you can see that this quantity right here is a volume differential d tau. So this whole thing then is J d tau, and so this turns into a volume integral. So the energy of the magnetic field now is 1/2 times the volume integral of A dot J, and that's d tau. I could have put a tau here. Now let's go back to the possibility of expressing J in terms of B, and to do that we just take Maxwell's equation for the cross product of B in terms of J, solve for J, and so we now have J equaling this quantity here. So we can take this and put it into this expression here. So here it is. Here's 1/2 mu 0. This comes about because of this 1/2 and the mu 0. So that's this part right here. And then here's A dot J. So it's the volume integral of A dot del cross B d tau. Now if you remember, we can write the expression for the divergence of a cross product in terms of this expression here. It would be B times del cross A minus A dot del cross B. Well, if this is the vector potential, then we have that this is equal to B right here, and so B dot B will be B squared. So that term is B squared. The other term we'll just leave as is, and so now we put this together. We have the first term being the integral of B squared times 1/2 mu 0. The second term will be minus 1/2 mu 0 times this volume integral here, and we change that the divergence of a cross product, we change to a surface integral here, and so we have a surface integral of A cross B dot dA. Now these have R dependences. This has an R dependence, and so does this. And the question is, if you make the surface larger and larger, what happens to these things? Well, as the surface S gets infinite in size, this all goes to 0. So the idea then is, if we take our volume large enough, we can get rid of this second term. So what that means then is that we can write the energy density, energy of the B field given by this factor times this integral here. And you can see that it looks similar to the electrostatic case where we would have an E squared here. Well, let's put them all together then. We have two versions of each equation. We have this one here, which deals with the charge density and the potential, or we have this one here that has the integral of E squared. Likewise, with the magnetic energy, we have this version, which is a function of the current rather than the charge density, and this one here, which is proportional to B squared. So you might think of these two being related to the sources of the magnetic field or electric field, and these are the results. Once you have the E field in B, then you can use these expressions. Well, we've used operator for the integrand of the integral to determine the density. So if we bring the 1/2 inside, so let's take this version here. If we take epsilon 0/2 inside, so we put it right here, or if we take 1/2 mu 0 and put it inside, then what we call the integrand will be the density. So here it is for the electric field, and here it is for the magnetic field. So for every point in the region that you're interested in, if we have an E field, this is the energy density at this point. And if you have a B field, then this is the energy density of the B field. And these can, of course, exist simultaneously if you wish. Well, the B field then has energy because it took work to create it. For an inductor L, this work is 1/2 Li squared. And the B field created by the current is usually inside the inductor, and it's surrounded by the current running through L. So therefore the B has some sort of finite surface through which it can be defined. Let's take a look at a piece of coax where we have current flowing down the center conductor in this direction, and we have current flowing on the shielding in this direction here, and we want to find the magnetic energy stored in the region between these two conductors, because outside the field is zero. It's also zero inside this conductor, so we only have this region in between, and so here we have a radius S between A and B. This is the expression we're going to use to find the energy, and so that's the energy density, and we've already said that B equals 0 outside of the piece of coax. Well, if we take and express this in terms of a fixed length, so we take, say, this length here, and multiply then by the integral of the dW sub B that we're going to get by just integrating the B field, then what we have is the length of the coax times, here's the B field right here. Remember, it's just 1 over S because we can use Ampere's law for the current inside. And so if we do that, we'll get the B field that's given here, just 1 over S. So putting that in, we'll have 1 over 2 mu 0, that's this one right here, times B squared. So here's B squared. And then we need a volume element, and this is 2 pi S ds times L. That's why the L appears in this equation. So let me repeat. If I multiply this by L, that will give us d tau. So separating everything out, we would have then this energy determined for the whole volume by doing the integral, and we have 1 over S, so we end up with a logarithm this side here. And notice that if you were to look at this, the only parameter that's here that you can change is the current. Everything else is fixed. So the inductor, or the source of the B field, ends up just being geometric and then an I squared dependence. Well, let's look at the case where we have L. So we're going to use this version of the equation. We've already done the L of a coax of length L, and that's this quantity right here, mu 0 L over 2 pi, and it's got the logarithm. So if we take and multiply by I squared, we end up getting the same expression that we have over here. Well, we can do the solenoid the same way, so we're going to use the same equation for the energy density. This solenoid has n turns per unit length, it has the same length L, and it has a cross section A. Well, we know that the B field inside is given by mu 0 n times I, where this is the number of turns per unit length. We know that B equals 0 outside. Well, we're going to assume that. And we're going to let A be the cross-sectional area of the solenoid. So if we take L times A, so L times this A, that will be the volume inside the solenoid. Well, because everything is a constant in terms of the various factors here, we'll just have, we don't have to integrate, we just multiply by the volume. And so we end up then with, forget this, 1/2 mu 0 n squared I squared times A L. So that's the energy contained in the magnetic field that's inside of this solenoid. Well, we can do the same thing with L. Here's the expression using the inductance in the current. And I want to remind you that when we look at the L in terms of deriving it, we have to take into account that we have capital N turns, and each one will couple to the flux. And so the inductance then will have this multiplier here, and then it'll have mu sub n times A. This is what we derived for the solenoid. Well, capital N is equal to little n times L. So we can come back here and look at L again. And so here's our flux per unit I, and that will be equal to NL mu sum 0 NA. So we've got two little n's, and so grouping those like this, we have the inductance. So putting that back into the 1/2 Li squared equation, we end up with this expression right here, and if you compare that with up here, it's the same as above. So you can see that approaching this from inductance or from knowing the field, we end up with the same quantity for the magnetic energy. And don't forget, what we're talking about is the energy of the field that's inside of this solenoid, because that's the only place where B is not equal to 0.